today what I want to do is more or less to talk a bit about some moduli spaces related to G bundles on smooth projective curves. So since we're going to do a bit of moduli theory, I think that to start with, as some kind of background and motivation, I would like to talk a bit about the moduli of curves. In some sense, I think this is the first moduli problem that was studied chronologically, although, I mean, it depends on what you mean by moduli problem. But let me just tell you more or less what the idea is. So in moduli theory, we want to classify different type of algebraic structures, or like some kind of algebraic objects. And in this case, for the moduli of curves, we're interested in classification of smooth projective connected curves. Oh, maybe I should say from the beginning of the talk, I'm going to work over the complex numbers. Most of the stuff that we do holds over a general Noetherian base, but I'm just going to work over the complex numbers. That's okay. Okay, so how do we classify this type of thing? Well, first, topologically, we can just classify it by the genus. So compact, orientable, closed manifolds of dimension 2, they are classified by like the number of holes topologically. They are classified. Genus G. So topologically, there's a single closed, compact, connected, orientable surface. We can call it XG. And then maybe the first question that can arise is how many complex structures, or how many like Riemann surface structures can we put on XG? So maybe a question is how many complex structures or Riemann surface structures up to isomorphism can we put on XG? So this is kind of like counting how many curves of genus G there are. And then we learn like fairly quickly in algebraic geometry that the answer is for genus bigger than or equal to 1, there are infinitely many. In some sense. So so the question kind of arises of, okay, that's kind of not that great of an answer, maybe if we were hoping for a number, but can we somehow measure how many of these there are? And the answer comes in terms of a classification problem. So like this is solved by Riemann's moduli space. So there's a way in which we can kind of put some structure in the set of all such complex structures. It's called Riemann's moduli space. So I'm not going to do any markings today. So let me just say for G bigger than or equal to 2, there is a complex variety, in fact, an orbifold, MG, and it classifies. So let's say parametrizing. Let's say complex structures on XG up to isomorphism. And we can see that as the genus grows, then there's in some sense more complex structures, because one can compute the complex dimension of this complex variety, or like, you know, this complex manifold or orbifold, if you prefer. I mean, it's not a manifold for like, yeah, but the singularities are quite mild, and this dimension is 3G minus 3. So we see that the larger the genus gets, then in some sense, the more complex structures that we have. So one, well, I wouldn't say problem, but like in moduli theory generally, one problem of this type of things is they're not compact. So this is a quasi-projective variety. If you take the core space, it's not a projective variety. In order to understand this thing, or this moduli space, the Lehrman-Mumford used two kind of very powerful ideas that I think have become quite standard in moduli theory. So I just want to tell you a bit of two kind of techniques that one generally uses in moduli theory in order to understand moduli spaces. So here are some techniques. And in some sense, I think to this moduli problem, they were very successfully applied by the Lehrman-Mumford. And there's some other people also, I mean, just to name two people that developed this type of thing. So the first one is compactification. We have a quasi-projective moduli space, and one might wonder, is there a natural compactification? Is there a natural projective variety that contains this as an open? So in this case, there's like mg, since inside of the moduli of stable curves. And this is a compactification. And the second one is a recursive understanding of the boundary. So the boundary, so this closed boundary that of all curves that are not smooth, they can be understood in some sense by gluing curves of lower genus. So roughly the picture that you should have in mind is we have this compactification, mg bar. Inside we have kind of the regional moduli space that we were interested in. This is mg. And then somehow this boundary admits some type of stratification. And the strata can be understood nicely in terms of lower genus information. So curves in lower genera. Okay, so these are the two type of structures that I want to emphasize. And these are the type of things that we're going to be looking for in other moduli problems. So whenever you have this type of structure in your moduli theory, then it's very useful in order to understand the geometry generally. So this was, for example, used in order to prove that this mg is irreducible. Okay, so maybe we can come back to kind of the original question that we had, which was how to count. And now actually this compactification provides us with some kind of answer to it. So a way of somehow measuring how many complex structures we have would be maybe computing a volume. So now that we have a compact thing, what we could do, for example, would be fix a top form integrating over this moduli, and somehow this would be like some kind of count of how many curves we actually have. So the bigger the volume, the larger the moduli space, somehow we can say the more complex structures that we have. In some sense, there's like a slightly different algebraic approach to counting via index theory. So instead of kind of computing a volume, what we can do instead is computing some shift cohomology. So there's k-theoretic counts, which says, okay, instead of computing a volume in the moduli space, you can just take some so-called k-theory classes and compute the Euler characteristic, just shift cohomology or some shifts on the moduli space. So a k-theory class is going to be something like a formal combination of some vector bundles on the moduli space. And then the index is just going to be, well, the Euler characteristic. So this is two ways in which you can kind of make sense of how many complex structures you have. You can try to compute a volume, or you can maybe try to compute some C cohomology groups on your moduli space. Okay. And maybe I should say that since we're already here, that there's a slightly more general. So this is in some sense Gromov-Witten theory of a point, but more generally, Gromov-Witten theory concerns itself with morphisms from, so let's fix X a projective variety. And then we have the moduli of morphisms or maps from genus G smooth curves with some topological invariant. And then this can be compactified into the so-called moduli of stable maps. And again, you can kind of play the same game, like trying to compute volumes of forms on this compactification, or trying to compute indexes of K-theory classes. And this is in some sense counting how many curves there are in this, a virtual count of how many curves there are in this projective variety. Okay, so today, the main emphasis, or kind of the main thing that we're going to be looking at, is instead of maps into a projective variety, they're going to be gauge maps. So they're going to involve some kind of symmetry. So today we're going to look at gauge maps from Riemann surfaces or from curves. So in some sense, the slogan will be that we're counting curves on some quotient stacks. Not necessarily like tame, or just they're just going to be algebraic stacks. So positive dimensional stabilizers generally. Okay. In fact, I think my main example is going to be like always positive dimensional stabilizers. So let me just give you the setup a bit. So instead of mapping into a projective variety, what we're going to map into is the following. We're going to have an affine variety. Take an affine scheme. I mean, reduceness is not very important in this case. We're going to have a reductive group. And maybe I should say that all of this works more generally for projective over affine variety. So instead of X affine, you can take X projective or X projective over affine. So the usual setup of GAT. But then the answer of everything that I'm going to say is a bit more complicated. So I'm going to stick with affine. So a reductive group, I don't know. So it doesn't need to be connected. So it could be a finite group. It could be a GLN. It could be SLN, SON, etc. Okay, and now we're actually not going to let the Riemann surface vary. There's something to be said there. That will be like a different talk. But for now, we're just going to fix. So C is going to be a fixed Riemann surface, or fixed, smooth, connected. You don't need connected, but okay, projective curve. Okay. And then let me just give you the main moduli that we're interested in. So the moduli that we're interested in is maps from C into X, but taking into account these additional symmetries. So this reductive group is going to act on X algebraically. And what we want to do is we want to map C into X, but somehow taking into account this equivariance. So some equivariant when with respect to this action of G. So we're going to consider maps from C into the quotient stack X mod G. So this is the main moduli problem that we're interested in. And I mean, just to be concrete, this parameterizes the following. So it parameterizes pairs ES, where E is a G bundle on C, and S is a section of the associated fiber bundle with fiber X. So we have this G bundle, and we can create okay, generally it's done in the opposite order, but I'm just going to stick with that. We can create this fiber bundle where we use the action of G and we twist by this G bundle. We have a fiber bundle over C with fibers isomorphic to X, and we're going to have a section. So they are pairs of this type of data. So you should think about this as some kind of moduli of G bundles with some additional decoration in a very general sense. Okay, so maybe the motivation for this is, in some sense, many projective varieties come from starting, well, I wouldn't say many, but interesting projective varieties come from starting with an affine variety with an action of a reductive group. You fix some type of additional data called an equivariant linearization, and you can take the so-called GAT quotient. And out of there, you can get many interesting examples of projective varieties. And you can ask, okay, what is the Gromov-Witten theory, or like how can we count curves instead of these varieties? And an idea that has been there for a while and like developed by many people in different contexts is trying to do something in the stack case. So instead of computing this so-called GAT quotient, you can just take the so-called stack quotient, which is what we're doing here, X mod G. And then if you somehow are able to develop some enumerative theory or to count curves on X mod G, maybe by taking some stability parameter to infinity, you can, via wall crossing formula, relate the counts, these stacky counts, counting curves into the stack, into Gromov-Witten theory of the GAT quotient. So that's kind of one motivation, and at least for genus series, kind of made precise by this work of Gonzalez and Woodward. But let's just say that, like, from now on, I'm going to ignore completely the enumerative geometry. I'm just going to focus on the geometry of this moduli space. But I just wanted to say something of like why you might be interested in this type of thing. But another source of motivation would be like a lot of classical moduli theory comes in this form. So there's a lot of like classical moduli spaces that are of the form, okay, G bundles on a curve with some extra decoration. Okay, so the goal is going to be the following. For the rest of the talk, I'm going to try to explain that one can describe some stability conditions, whatever that means. I'm going to try to explain what that means. One can build moduli spaces of semi-stable objects. This is going to have a generalized Hitchin fibration for any such X and G. And then we're going to have a stratification that emits a recursive structure similar to the so-called Kesselink-Kirwan stratification of GAT quotients. And using that, we're going to be able to compute indexes. So we're going to compute Schiff cohomology, generalizing the Verlinde formula that is usually done for G bundles and then generalized for Higgs bundles. We generalize to this like more general setting of decorated bundles. Okay, so that's more or less the goal of this. Let's look at some examples to kind of motivate what I'm going to say. So I would say one of the simplest examples is when X is a point and G is just the general linear group GLN. So in that case, a map from C into point mod GLN, well, that's the same thing as a map from C into the classifying stack. And that's just the stack of rank n vector bundles on C. So it classifies vector bundles of rank n. And then just for the purpose of not saying connected components everywhere, I'm going to say that topologically we can have some invariants. So topologically, oops, let me just say that there are some clear topological invariants. That's going to be the, how do I, okay. The degree of vector bundle on the curve. So we're going to fix it. We're going to call it D. Okay, so now one can try to replicate this. So is there, I mean, this is parameterized by a stack, or like, if you prefer it, I mean, for me, stack tautologically means moduli problem. We have this moduli problem. Can we somehow parameterize it in terms of a complex projective variety as before? And the answer is no. So the main problem that we encounter is there is no complex projective variety that classifies in a suitable sense, or in a reasonable sense, all vector bundles. And generally, there are two solutions to this problem. So you have solution one. You just work with the whole stack. Of all rank n vector bundles on the curve of the greedy. The other solution I think originally due to Mumford with following work with like Cesadri, Narasimhan, and a lot of work on this, is instead of looking at all vector bundles, we can restrict. So there is a special type of vector bundle. So there is a class of sufficiently rigid vector bundles called semi-stable vector bundles. And they are parameterized. Or let me just say, up to a mild form of up to a mild equivalence relation, they are classified by a projective moduli space. So by a projective complex variety. Once you fix the degree. Okay, so I think the picture that you should have in mind is something like this. You have this huge thing, parameterizing all vector bundles. That's kind of like Van and C. And then inside, you have this small piece, which are the, let me put the degree, which are the semi-stable vector bundles, those that can actually be parameterized by a complex projective variety. And then you have, in the boundary, you have kind of the wild world of all unstable vector bundles. Okay, so now maybe one question can, well, we can ask the same question again, which is how do you count semi-stable vector bundles? And again, there are infinitely many. This projective variety tends to be of positive dimension, so you know, has infinitely many complex points. But actually, there's a different way in which we can interpret this question in this case, which is maybe passed to finite fields. So if you consider curves over like if you fix a curve over a finite field, you can actually try to count how many vector bundles, semi-stable vector bundles there are. So how to count? And so the first approximation could be like over finite fields. Or maybe trying to compute the cohomology and then like computing weights. That's, you know, via Frobenius trace related also to like these finite fields. So you can also make sense of that over the complex numbers in some sense. So over finite fields, this was this was attempted by Harder and Narasimhan, and this is how they did it. In some sense, you can understand the count over a finite field over the whole stack, so over this big object. And then you want to relate the count over the whole stack to the count of just semi-stable ones. In some sense, the thing that is parameterized by this projective variety. And how do they do it? Well, they use the same strategy as Delina and Mumford. You have this compactification. In this case, the compactification is a bit weird. You just have this big thing. You have this boundary. And what they do is they stratify. So they construct a stratification of the boundary. And again, it can be understood. So its strata, in some sense, can be understood in terms of semi-stable vector bundles of smaller rank. So it has this recursive type flavor. And what you can do is you can take this boundary. You can again stratify. It's an infinite stratification. And in order to understand counts over the semi-stable locus, what you can do is you can count over the whole stack. That tends to be easier, and then somehow control the error terms recursively by subtracting the counts of these additional strata that you're overcounting. Okay, so that's over finite fields, but it turns out that this strategy over finite fields can also yield to analogous counts over the complex numbers. So over the complex numbers, well, I'm just going to stick to the K-theoretic picture. So how can we compute indexes of K-theory classes, or just sheaf cohomology of some nice sheaves on this moduli space of semi-stable vector bundles? Well, it turns out that there is some nice class called the determinant line bundle. So there is a nice line bundle. I don't know, I think, okay, maybe the adjective. There's a line bundle. I'm not going to make any judgment about how it is. A line bundle L called the determinant line bundle. On this moduli space, let me just call it M, moduli space of rank n, degree D, semi-stable vector bundles. And then it turns out that there's a nice formula for the index of this. It's called the Verlinde formula. So it turns out that this line bundle doesn't have any higher cohomology. So the Euler characteristic is just the dimension of H0. And what the Verlinde formula says is that the dimension of H0 of powers of this line bundle can be understood in terms of a concrete formula, which I think, I mean, I find the formula quite like nuts. Okay, I'm gonna need to like, I don't know this by. Okay, so just bear with me for a second. I just want to have the formula up so that you can admire how on earth this is an integer. Okay. Okay. Here, G is the genus of the curve, and D is the degree. And this formula is in the case of rank 2. So I just put you the case when n is equal to 2. So yeah, you have this weird combination of signs, and then it turns out that it's a positive integer, and it's the dimension of, it's the dimension of this sheaf cohomology group. Okay. So yeah, so we have the kind of a similar story for vector bundles. We have the stratification, the compactification. We have some sense of counts, and there are some results along these lines where one can compute indexes of K-theory classes. And I must say that this formula originally was obtained and then like proven using different techniques, either wall crossing or maybe some ideas from like fusion, so like topological field theories. But there's another proof by Telemann and Woodward, another strategy by Telemann and Woodward, where you can compute the index over the whole stack, and then you can control the error terms in some sense over the unstable strata using the Harder-Narasimhan stratification. So this is the kind of strategy that we're going to try to like use in the more general setting. So in some sense, the Harder-Narasimhan strategy also works to compute this type of indexes over the complex numbers. The analog story, but not over finite fields. Okay. So now, let me go to the second example. Because I want to introduce some kind of Hitchin fibration, generalized Hitchin fibration, and then we're going to have the main result. Okay, just for simplicity, let me take g is equal to 1 so that we don't have to have a twist. Otherwise, you can incorporate the twist in this setup, but like I don't want to worry too much about it. So C is going to be an elliptic curve. X is going to be the Lie algebra of the reductive group, and or the total space of this vector space, thought of as an affine variety, and it's going to come with an action, the adjoint representation. So it's going to come with a linear action of G. Okay, so now in this specific case, where are maps from C into X mod G, or into, sorry, let me just G mod G. Well, these are somehow going to parameterize a G bundle, E G bundle on C, and then you're going to have a section of the so-called adjoint vector bundle. I mean, this is just by definition a section of the associated fiber bundle with fiber the Lie algebra under the adjoint representation. So these are called generally Higgs bundles. In this special case where the genus is equal to 1. Okay. So there's a similar story. There's a Harder-Narasimhan stratification. This is a bit more recent. But the main problem here is that the moduli space is no longer projective. So you don't expect to just take a line bundle on the moduli space and being able to compute an Euler characteristic, because if the moduli space is not projective, the cohomology groups are not going to have finite dimension. How do you make sense of just taking the sum, like, you know, the alternating sum of the dimensions of the cohomology groups? So here's a different strategy. So we have similar story. There's a notion of semi-stability. There's a notion of like Harder-Narasimhan stratification, in particular, inside of this big space. Well, actually, how do I want to do this? Let me muse for a bit. Let me just say something. So we're mapping into X mod, or into G mod G. This is the stack quotient, but there's another way of computing a quotient, which is G mod G. This is the affine GAT quotient. This is just defined as spec of oops, I'm working over C. Spec of the ring of invariants, and there's a natural morphism from the stack into this affine GAT quotient. Okay, so let's just use functoriality. So if you have a map from C into X mod G, or again G mod G, well, if I just compose with this morphism, what I'm gonna get is a map from C into G mod G. But now this is literally an affine variety. C is a projective smooth curve. Any morphism into this affine variety just factors through a point. So actually morphisms from C into G mod G is just the same thing as specifying the point where this curve maps to. So we have a morphism from our moduli problem into this affine GAT quotient. Inside of here, we have the morphisms that are semi-stable. So the semi-stable Higgs bundles. I said that this admits some kind of moduli space. We can call it M Dolbeau. And then it turns out that by some universal property of moduli spaces, this morphism from the semi-stable to the GAT quotient is also going to induce a morphism from this moduli space into this G mod G. And this is generally called the Hitchin fibration. So, and it turns out that if you fix the degree of the G bundle, there's a notion of degree of a G bundle, then this morphism is proper. So if we have a sheaf on M Dolbeau or a K-theory class, we can push forward to a nice K-theory class on G mod G. That makes perfect sense. So maybe the way to try to understand this is, okay, this moduli space is not projective, but is projective over an affine thing. So the best thing that we can do is to take the K-theory class, push forward to this affine thing, we get some kind of K-theory class there, and we can try to understand what this K-theory class is there, or to try to somehow extract an index out of it. And let me just say that there's an action of the multiplicative group on the moduli of Higgs bundles. You can scale the Higgs field, and similarly, there is a multiplicative action here, and this morphism is equivariant. So somehow we have this class, we push forward to the affine thing. Over the affine thing, we can't really compute an index, but we have this GM action that kind of contracts. So we're kind of in a similar situation as the projective case, where we can think of this as like graded, as a graded ring. We have this K-theory class, which you can think of as a sheaf, a graded sheaf, like, you know, graded sheaf of modules for this graded ring. And maybe instead of computing the index, which doesn't make sense, we can compute the index of each graded piece. So that's the main idea. So an idea is, if you take K-theory class on the moduli space or in the moduli stack, it actually doesn't make much of a difference. That is GM equivariant. Then you can push forward, and you can get, you can push forward and you can get a GM equivariant K-theory class on the affine base. And now, so push forward. Graded K-theory class on this affine thing, and then the index of each grading, or like its weight, is finite. So in some sense, instead of taking a single number, which is the Euler characteristic, what you can put is, you can put all of these together into some kind of generating series. So the nth coefficient will be the index of the nth graded piece. And then an analog of the Verlinde formula in this case would be somehow given an explicit formula for this generating function that encodes all of the indexes of the graded pieces. And this was done. So Verlinde formula for Higgs bundles. They didn't have this assumption that the genus is equal to 1. So this would be for any genus. This was due to two sets of authors. So it was independently obtained by Andersen, Gukov, and Pei. And around the same time, so this was around 2018, it was obtained by Dan Halpern Leistner. And again, you get some kind of formula involving some complex exponentials. Same thing as we said from before, we had some kind of signs, which are like some combination of complex exponentials. So kind of weird combination of transcendental functions that computes the indexes of these classes. And I must say that this Verlinde formula is, again, you can do it for the analog of the determinant line bundle here. You can build the same determinant line bundle for this moduli space. Okay. So we have these two examples, slightly different, but pretty much the same. You have the same type of structure, geometric structure. You have the same type of results. And then I guess the main result is going to be that all of these are special instances of this more general story for any class of moduli problem that involves decorated G bundles. So so let's go back to general map from C into X mod G. And I must say that the same thing as before, you have map from C into x mod g, and this maps just by functoriality into the affine GAT quotient, which you can just express as this. So we're going to call this kind of the generalized heat-sink vibration. And then we're going to need some stability conditions. So we have a kind of more general version of stability conditions, but I think the easiest to describe is the following. Let's fix chi to be a character of this reductive group. So this is the generally the type of data that you fix in order to do GIT. So this is roughly stability condition in the sense of GIT. For this quotient x with an action of g. So out of these, you can get a semi-stable locus inside of x, and you can just run the usual notion of GIT. And the idea here is that we're trying to do it kind of globally over the curve. So instead of just looking at the x mod g, we're looking at maps from x mod g. So in some sense, points of x mod g parameterized by this curve as it varies. Okay. So that's, I mean, you can take this to be just the trivial character, but then things are not that interesting. And it's important to have, as I said before, these parameters that you can take to infinity in order to relate some of these enumerative counts with something that you would expect be Gromov-Witten theory, like, you know, quantum K theory of the GAT quotient. Okay. So now we're ready for the theorem. This is joined with Halpern-Leistner, and it says the following: for any x g chi as before, we have the following. So first, we have a stability condition, and we have inside of the stack, we have a chi semi-stable locus. So this open piece. How do I want to do this diagram? Let's do this like this. Okay. This is going to admit a moduli space, and it's better if you fix the degree generally. So this is going to have a moduli space. And it's going to have this proper morphism into this affine. So this is called, what you can call this the generalized heat-sink vibration. So for any of these moduli related to like G bundles with decoration, you can build a semi-stable locus, and you obtain a moduli space that is proper over X mod G. And I should say that this is not the main emphasis of this talk. This was also obtained by GIT, maybe for slightly stricter notion of semi-stability by Schmidt. So our approach is slightly different and a bit more intrinsic. So we use like some of these recent stack theoretic intrinsic construction of moduli spaces to obtain this. So that way we work directly with the stack. We don't have to do all of these like reduction steps. Okay. Now I would say this is the main theorem, which is there is a harder Narasimhan stratification of the unstable locus. And it can again be understood recursively in terms of, in some sense, lower complexity data. So if you know the Hesselink Kirwan stratification of X mod G, you know that there's some strata. The strata looks like stacks. For like some co-character, you have a subvariety modulo the action of a parabolic, and then that admits a morphism into, well, another quotient stack, which is an action of a subvariety modulo the Levy. And in some sense, the Levy is a smaller reductive group. And then many times you can use this to do some kind of recursive arguments. The same story applies here. So you have an infinite set of co-characters that we can actually more or less describe or like index. For each one of these, you have a strata that again looks like a mapping stack from C into the same type of Kirwan stratum. But like it's not a Kirwan stratum for X mod G, like you can have many more. I mean, you can have infinitely many. And then again, you have some kind of retraction into something that looks like a mapping stack into some other X modulo some Levy for some modified stability. And then the name of the game is kind of using this to relate information about this like bigger group in terms of smaller groups and getting recursive formulas that way. But many times you don't even need the recursive formula. You can understand very well how the strata looks like, and you can prove that just all of these error terms of the stable part, they vanish. So if you compute something over the whole stack, it's the same thing as computing over the semi-stable locus. Quantization commutes with reduction of Telemann. Okay, so here's an application of two. This is a Verlinde formula for for decorated bundles. So let's assume, so it's easier for simplicity to assume that X is a linear representation of the group. So this includes the point, and it includes also the adjoint representation, but you can do many more. For example, Bradlow pairs or stuff like that if you take the standard representation. Okay, then there is an explicit formula for the index of some special K-theory classes. They include the determinant line bundle among them. They are called Atiyah-Bott classes. This is in the graded sense. Okay, so I'm not going to try to put the formulas. They are quite like, you can take a look at the archive paper, but so what I'm going to say is you have these very nice universal tautological classes in the stack of G bundles. It turns out that in some sense they generate the cohomology. You can pull them back to this stack of G bundles with some extra decoration. You get some K-theory classes. They are GM equivariant for the scaling action of GM on the linear representation. When you push them forward under the Hitching morphism, you get some kind of graded module there. You can take the generating function with respect to this grading. And what one can get is, okay, over the whole stack, you can get explicit formulas for these generating functions, again, in terms of like some complex exponentials. And then we give criteria. First, we give recursive formulas to relate the computation over the whole stack to the computation over the semi-stable locus. And in nice cases, we're able to kind of explicitly say when all of these error terms vanish. So when you actually get an explicit formula for also over the semi-stable locus. So this is the case, for example, for the determinant line bundle. But there are other, like in the usual Verlinde setup, but there are some other K-theory classes where depending on the group and depending on your X, you're able to kind of like give a bound on how, in some sense, positive your level has to be in order for there to be no error terms. Okay, so this is the main, this is the main theorem, which is in some sense like expanding these ideas of compactification, stratification, etc. So maybe just in a couple of minutes, I could give a sense of how, or maybe just say a bit about like what ideas come into the proof. I think I already said aloud, but maybe too quickly. But if you're interested, I can say more about that. I said a bit about how this stratification looks like. It looks like it's going to be quite useful in general if you want to try to understand the geometry of these things beyond computing indexes of K-theory classes. So for wall crossing purposes, is in terms of indexing, when X is a linear representation, is like just as nice as the Kirwan stratification. Just the combinatorics is a bit more complicated, determining which co-characters appear. And there's infinitely many co-characters again, because naturally the stratification is infinite, like in the case of point mod GLN. But let me just say a bit of like ideas of proof. So the proof basically proceeds via two things. The first kind of thing is some wall crossing ideas. So here's the deal. It's actually quite difficult to find like this Harden and Narasimhan stratification for this general X. So maybe in examples you can think like Higgs bundles, G bundles, etc. is not too bad. But you lose quite a lot of structure if you just consider a general X. So like if you try to look for somehow a maximal destabilizing parabolic reduction compatible with like the extra decoration, it gets a bit like complicated. Especially like, you have these random decorations. So here's an easier thing to do. What you can do is you can compactify X, G equivariantly. And then in some sense, you can construct a compactification. So again, we have this compactification idea. So using Conceived stable maps, there's this idea due to Gonzalez and Woodward, where if X is projective, you have another stack called the stack of gauge maps, again, into X mod G. And the main advantage of this is that this is proper over the moduli of maps into point mod G. So you have a morphism from X mod G into point mod G. This gives you by functionality a morphism into the stack of G bundles on C, and this is proper. The fibers are proper DM stacks. Now, the main idea is here we have an extra stability parameter. So we have the original chi, but we have maybe another one. How should I call it? C. And for this compactification, I shouldn't call it maps because it's really not maps. It's like slightly, in the sense that like conceived stable maps are not maps. Let me just call it. No, because I mean the curve is fixed. Let me call it like this. I think this is literally the notation that we use. Okay. So we have this. Oh, what happened? Well, okay. Yeah, everything is compactified. So we have an extra stability parameter here. The idea is because of properness, we can we can build a stratification, understand the stratification quite well in this somehow compactification of it. And then maybe like if you're paying attention, like generally you cannot compactify X mod G equivalently. So really this is a compactification relative to the GAT quotient, to the affine GAT quotient. Okay, so because of properness, we can understand this and relate it to Harder-Narasimhan of just the usual Harder-Narasimhan of G bundles. And then we take this parameter to infinity, this parameter somehow measures how far is your mapping to landing inside of X. So like how big is the part of your curve that maps to the boundary, X bar mod X. And if you take this parameter to infinity, very, very roughly, what happens is we understand how this stratification behaves. Eventually, the stratification stabilizes, and when you restrict the stratification to this open, you get the stratification that you wanted to have it from the start. So the idea roughly is some kind of wall crossing. You compactify, and then like you kind of start taking some parameter to infinity, you see how it behaves, and eventually just stabilizes. And then like when you restrict to the open, you recover what you had. And this is the wall crossing idea. The other idea is, maybe I should just say that this would take maybe another talk, but we have this this idea of infinite dimensional GAT, where roughly, so this was developed with joint work with Halpern, Leistner, and Jones, and also so there we did it for torsion free shapes in higher dimensions, and then for G bundles in higher dimensions, we with Gomez and Zamora, and the main idea here is roughly check implicit criteria for existence of moduli spaces. So generally, how you can do it is using usual GIT. So you choose an embedding of your moduli problem into into some quotient stack. Hopefully, like your semi-stable locus all lands in there. So you have to prove some boundedness, and then you prove somehow that this nice quotient stack, the semi-stable locus mod G, has the nice conditions that you need in order to have a geometric quotient, also not a geometric quotient, a good quotient in general. So here, there has been some recent progress in having some implicit criteria for determining when a moduli stack has a good moduli space. So it's like two conditions called like S completeness and theta reductivity. And what we do is we can check them, but instead of choosing an embedding into a GAT problem, instead we do it implicitly in the stack by using local uniformization by affine Grassmannians. And I should say that you don't need this in order to build a moduli space. As I said, if you are very clever with GAT, you can get the moduli space just purely using GAT, but the harder Narasimhan stratification, which is the really new part of these results that I'm announcing, that you can't really use using GAT. So you need to use this kind of like more recent techniques of Halpern, Leistner, and then Halpern, Leistner, and Heinov working intrinsically with the stack. Okay, sorry, I think I didn't say much about the steps, but let me just leave it at that because I think it's more or less like out of time. Yeah, thank you.